You know, AI is everywhere. It's in the shows we stream, the routes we drive. It's even getting into things like medical diagnosis. But here's the big question. How do we actually know we can trust it? Well, it turns out there are these hidden rules, a kind of secret code that separates a truly reliable AI from one that's just a dangerous illusion. So let's pull back that curtain and see what's really going on.
So picture this. A team of data scientists has been working for months on a new AI model. They test it, they tune it, and the results? They're just incredible. I mean, it's hitting 99% accuracy on all their test data. It really looks like a breakthrough. But what happens when you finally open the lab doors? Because all that incredible accuracy, it can just vanish, like in an instant. And this right here is probably the single biggest challenge in building AI we can actually count on. It's this massive gap between what a model promises in a safe, clean environment and what it actually delivers out in the wild. And look, this isn't just some abstract technical problem. It's a crisis of trust. When a model that seemed absolutely perfect during development suddenly starts making huge mistakes in the real world, well, the consequences can be enormous. There's this giant gap between how a model performs in the lab with its perfect, controlled data and how it does in the messy, unpredictable real world. It happens because the model hasn't really learned the underlying patterns. Instead, it's just gotten really, really good at acing the test on one very specific, clean data set. This is why so many AI projects end up failing. And it all boils down to this fundamental balancing act. Yeah, this all comes down to a crucial idea in machine learning called the bias-variance tradeoff. Think of it like you're studying for a big exam. A model with high bias is like a student who only skimmed the chapter summaries. They get the big, simple ideas but miss all the important details. They've underfit the material. On the other hand, a model with high variance is like the student who memorized every single word of the textbook, right down to the typos. They've overfit. They're useless when a question is phrased even slightly differently. The goal is to find that perfect sweet spot. And let me tell you, that is the hardest part. And that second problem, overfitting, oh, that is the real villain of our story. It's how an AI model can, for all intents and purposes, lie to you. It promises this incredible performance, all while hiding a catastrophic flaw. Let me show you exactly what I mean. Okay, take a look at this chart. On the surface, this model looks like a huge success. It was graded with a standard metric called Q2, which basically measures its predictive power. It got a score of 0.71, which, in this world, is a pretty solid grade. You'd look at this and think, yep, this is a good, reliable model. But looks can be incredibly deceiving. Turns out, it was all an illusion. The moment this very same model was put through a correct validation process, its score just plummeted to negative 0.15. Now, that's not just bad, that is worse than a random guess. The model wasn't just wrong, it was confidently and consistently wrong. And it all happened because of a critical error called data leakage. Data leakage is pretty much what it sounds like. It's when some piece of information from the future, or from the test itself, accidentally leaks into the training process. So the model isn't really learning how to predict anything, it's learning how to cheat. It's like it got a peek at the answer key before the test even started. So how do we stop this? How do we catch these lying models before they cause real damage? Well, this is where our hero enters the story. A rigorous, non-negotiable set of rules for model validation. And these aren't just, best practices. They are the absolute essential principles for building AI that won't betray our trust. And these rules are actually deceptively simple. First, you have to lock your test data away in a vault. It cannot be touched, seen, or even sniffed at while you're building the model. Second, your tests have to be a dress rehearsal for the real world. Third, you have to grade the model with the right scorecard for the job. And fourth, you always have to check if your fancy, complex model is actually any better than a much, much simpler one. This quote right here, it just nails the heart of rule number 2. It's not about how well your model does in some perfect theoretical world. What matters, the only thing that matters, is how it's going to perform in the messy, complicated, and totally unpredictable future it's actually going to have to face. So what does testing for the real world actually look like in practice? It means we have to go way beyond just splitting our data once and calling it a day. It means using more robust, more clever techniques that are designed to really reveal a model's true character. A really key technique here is something called cross-validation. So instead of just one training set and one test set, imagine you split your data into, say, 5 chunks. You train the AI on 4 of those chunks and test it on the 5th one. Then you swap which chunk is the test group and you do it again and again and again until every single chunk has had a turn being the unseen test data. This forces the model to prove itself over and over. There's no getting lucky with one easy test. Which brings us to rule number 3, using the right scorecard. Now, look at these two charts. This is wild. They show the performance of the exact same model. On the left, where the data is nicely balanced, its performance looks rock solid, super stable. But on the right, with highly imbalanced data, which, by the way, is super common in the real world, its performance is all over the place. The way we were measuring success suddenly became totally unreliable. So here's the crucial point. The context of the problem defines the metric. Think about it. In medical diagnosis, a false negative telling a sick person they're healthy is way, way worse than a false positive. A simple accuracy score completely hides that critical detail. Your scorecard has to reflect what actually matters in the real world.
When you put this all together, all these rules, they point to one big, crucial idea. This isn't just about following a technical checklist to get a better score. It's about a fundamental shift in how we think, from just building a model that works in the lab to building one that is truly trustworthy out in the wild.
And that really is the ultimate takeaway here. Proper, rigorous, painful in a good way validation is the absolute bedrock of reliable AI. It's the one thing that transforms a cool but brittle tech demo into a robust, dependable tool that you can actually deploy to solve real problems and maybe even change the world for the better. So the next time you see a big headline about a new AI breakthrough, or you use a tool that's powered by machine learning, you'll know to ask the right question. Not just, hey, how accurate is it? But how was it validated? Because the answer to that question, that's what tells you if it was really built to be trusted.